Howdy. The point of this video is to discuss how to index directions in crystallographic space. Now, why would I want to do that? There are a few different reasons. One would be if I want to describe anisotropic properties of a material. That is, some property, say electrical transport, that depends based on what direction I measure it in a single crystal. So one example of that is if I'm measuring the conduction, the electrical transport in graphene. If I measure it in one direction this way, or in this direction, I would get the same result. However, if I measure it in some other direction, I'm going to obtain different physical properties. So that's what we call an anisotropic material. Another reason is that maybe I want to describe the orientation of different crystals relative to each other in a polycrystalline material. So this is using a technique called electron backscatter diffraction, and really what this lets us do is look at the crystallographic orientation of these different grains. And so how I show their orientation relative to each other is by illustrating the direction of the grain that's coming out of the plane. And I'm giving those a color based on this three-dimensional color scheme here. Finally, something we'll talk about quite a bit later on is close-packed directions along close-packed planes. And these are important because slip happens along these directions. And so in order, again, to talk about these, I need to know how to talk about directions in a crystal lattice. So let's try some examples here. I'm going to start off with a very general lattice. So this is a triclinic lattice. If you can do it in this lattice, you can do it in any lattice. So I have some direction that I'm interested in. There are a couple different ways to do this, so we're going to do them both. The first is using the head-to-tail method. And so basically, I'm describing this vector by subtracting the position of the tail from the position of the head. So again, remember, we talked about how to index points in space. The point of the head here is given by 1, 1, 1. The point of the tail is given by 0, 1/2, 0. Now, if you don't know how to do this, go back and review the video talking about indexing of points. So if I subtract the tail from the head, I get 1, 1/2, 1. Now, the final thing I need to do is to write this in the typical vector direction notation. And so what I want to do is remove any fraction. So I'll multiply through by 2. That gives me 2, 1, 2. And because this is a direction, I'm using square brackets to denote this. Okay, so another way to do this, same direction. Again, I can shift a direction. The absolute position is not important, just, again, the direction. So these two are equivalent. But if I take any direction and I shift it such that the tail is sitting on the origin, then if I'm using the head minus tail method, I'm subtracting 0, 0, 0 from the head position. So this is sometimes a little bit easier. So I shift the direction so that the tail sits on the origin, and then all I need to do is figure out the fractional coordinates of this head position. And so in this case, it's 1, 1/2, 1. Again, if I want to write a direction, I want to use integers, not fractions, and I need to use a square bracket notation. So I multiply this whole thing through by 2, I get 2, 1, 2, and I use square brackets. And this is how I would denote this particular direction that I'm showing. And notice that this is the same thing we got using the previous method. Okay, now what about if you're given a direction and you're asked to draw that on a unit cell? So again, there are two different ways to do this. We're going to do these sequentially. First is if I want to keep this direction entirely within the 1 unit cell. And so this is essentially the exact opposite of the process that we just did. So I need to divide through so that all of these numbers are less than 1. So if I divide this whole thing by 2, I get 1, 1/2, 1/2. And this is going to be the position of the head of that direction. So I can start at the origin, and I can go to 1, 1/2, 1/2. So 1 is the fractional coordinate in the x direction, 1/2 in the b direction, and 1/2 in the c direction. And so this is a vector. It goes from the origin to the exact middle of this front face. Okay, let's try the other method. And in this case, I'm not going to reduce it so it's sitting entirely within one unit cell. I'm going to use, I'm basically going to extend and use the unit cell neighboring it forwards out of the plane here. And I can do the same exact thing. So again, this is going to give us the position of the head of the vector, and the tail is going to sit on the origin. So 2 is all the way down here, 1 is all the way up here, and 1 is all the way up here. And so this is a vector that goes from the origin all the way to this frontmost corner. Now you'll notice that this passes through the same point that we defined previously when we kept it in one unit cell. So the only difference between these two is the length of the vector. Oftentimes with directions, we're not the magnitude of the direction is not as important as the direction in the lattice, but sometimes it is. So in this case, the actual magnitude of 2, 1, 1 is given by this full vector.